Hello everybody, welcome to our second session in the Physics Teacher Virtual Summer School. Now this is a session that we ran at the actual summer school last year. Stuart did diagnostic questions and it was extremely well received. So I think you're in for something really good this afternoon. So I'm not going to hold Stuart up any longer and I'll hand over to him.
Okay, thank you very much, Gregor. As Gregor's already said, this is a session that I've done before at previous events. So hopefully, even if you have been along to some of them, there will still be things for you to take away. After last week's virtual summer school, where we had Chris Hooley speaking very much focused on physics, I'm afraid, or I don't know if there's anything to be afraid of, but this one is going to be much more focused on pedagogy, but obviously very much rooted in the context of physics and how we can actually improve the teaching of physics. Now, today we also have Alan Reid, the IOP Scotland physics coach, based up in Murray, who is acting as chat monitor. So he will be keeping an eye on the chat. So please feel free during the session, if you've got questions, if you've got comments and things to make, can you put them into the chat? There will also be times when I will be asking you to consider things or to respond to things where we would like you to use the chat. Obviously, in a face-to-face session, there would be times when I would get you into small groups and to discuss things. We're going to try and use the chat box as much as possible to replicate that, but obviously the dynamics are a little bit different. The big benefit, though, is of course with the real face-to-face summer school, only 20 people would have been able to attend. So I'm pleased to see that we've got well over double that number with us today. So thank you for joining us this afternoon. So just make sure that I've got my slides working. And before we look more deeply at diagnostic questions, I want to explore the topic of assessment in a little bit more detail. And here I think is a very good definition of what we actually mean by assessment. And this is the point that I normally say something fairly controversial. Bear with me, don't start throwing things at the whatever device you're watching or switching off, because I will qualify things a little bit later. I would raise the whole issue that I think perhaps we don't actually assess pupils often enough in Scotland. In physics, I think we've, in many cases, I know that that's a very sweeping generalization to make, but in many cases, I think that we perhaps don't assess enough. But as I say, I'll come and qualify that in a little while. So in terms of assessment, it's trying to get information about our learners. So why is this important? And well, as teachers, I know that you're probably all well aware that there is a big difference between what is taught and what is learned. And Dylan William is always a good person to get a good quote. And certainly in the field of assessment, there are a few people that are better placed to make statements. I'm sure you're all aware that along with Paul Black, he was the person behind Inside the Black Box and the whole sort of formative assessment for learning movement. Again, another book that I would strongly recommend, co-written between Paul Black and Dylan Williams and others. And things like Embedded Formative Assessment, which I know is a common book that many people have used, are excellent sources of information about assessment. But all as well and as good as a quote like that is actually concerned, I think the cartoon that I've put up on screen communicates what we're after much more effectively. So why assess? I've alluded to that a little bit. The quotations have alluded to that. And it's essentially the key thing is to find out what pupils have actually learned. And there are different purposes for this. So this is where I qualify my initial statement about us not assessing enough, because I think there are four key ways in which, or purposes that we assess. The summative assessment, we're all familiar with end of unit tests, with SQA exams, etc. The formative assessment, the stuff that I've just been talking about assessment for learning inside the black box, which we use to guide the sort of learning and where both teachers and learners progress. Diagnostic assessment, what I'm going to explore in a bit more detail this afternoon, and also accountability. Newspapers will always publish league tables. There is a lot of accountability pressures put on the education system from all sorts of different places. And unfortunately, that's one of the purposes of assessment. So going back to my comment about us not assessing enough, we do a lot of assessment, but I would qualify my statement by saying that the balance of our assessment is wrong, that we have got much too great an emphasis on summative assessment, end of topic tests, SQA exams, also more emphasis on accountability than ought to be the case. Formative assessment, I think, has improved, but again, I think the practices in a formative assessment often have been diluted. Like Dylan William himself says that he regrets naming the work that he's done about assessment for learning and so on, and would have, with hindsight, rather called it some things like responsive teaching to avoid I think the use of the word assessment. So there's quite a lot of that going on, but I think some of the practices might not necessarily replicate the sorts of effects that were first produced in the research that Dylan William and Paul Black did. But that leaves us with diagnostic assessment. And here, that's the area where I think we're probably not assessing sufficiently. And that if we were able to change the balance of our assessment away from summative assessment towards diagnostic assessment, I think my hypothesis is that we would actually improve the learning and the actual ultimate performance of pupils across Scotland. So let's have a look at this in a bit more detail. And I've put up on screen now 2 of the 10 principles of instruction from Rosenshine. I think Rosenshine's 10 principles of instruction give a very clear description of effective teaching practices. And it's interesting that 4 of them are very much tied into assessment and diagnostic assessment. Number 3 is about asking lots of questions. And again, that's an important part of diagnostic questioning, is to actually help us as teachers to find out what pupils actually are understanding, how they're interpreting things. It's important to ask lots of questions. And diagnostic questioning is all about checking for student understanding. And Rosenshine's principle number 6 is clearly about checking for understanding. Principle number 7, I think, also relates to the assessment that we're doing and how that impacts on the actual learning that takes place. And that is that we should be setting tasks for pupils to obtain a reasonably high success rate. And again, some of the research would suggest that the success rate that we should be aiming for is about 80%. If something's too easy, that will demotivate pupils, if they're being able to get it and, regularly scoring very highly. The lack of challenge leads to demotivation. Likewise, if something is too difficult, that is going to switch kids off. So trying to make sure that the questions that you're asking are likely to have a success rate of around about the 80% mark seems to be the sweet spot from the research. And then number 10 is about weekly and monthly reviews and giving practice. And again, this is something that I think that can be built into the assessment that we're doing and the formative assessment that we're doing on a regular basis. And that essentially comes back, I think, also to how we actually arrange our curriculum. So there's maybe some things that I'll go into a little bit more detail there in a moment. So having looked at Rosenshine's principles and identified how that relates to assessment, another key researcher that I would recommend is John Dunlosky. And he's written about improving students' learning on a number of times and occasions. And this important paper from 2013 actually highlights that what I'm talking about here, isn't news. That we've known about experiments, about practice testing and the effect that that has on learning for well over 100 years now. So let's have a little bit of a look at the evidence. Now, I'm not expecting you to read these graphs. I've obviously cut and pasted them from the papers. All that I would like you to be able to see on screen at the moment is the relative height of the dark bars compared to the light bars on the bar charts, because that's the key message. That the key message here is that if pupils engage in some form of practice testing on a sort of regular basis, they will outperform pupils who just do further restudy. The kids that read over their notes and do other forms of learning activities will perform less well than kids that engage in recall and practice testing. So the dark bars are the performances using practice testing, as opposed to the lighter bars where pupils have not done practice testing and doing regular questions, but just doing other forms of more traditional study. And the message, as you can hopefully see from all the bar charts, is that the dark bars, the practice testing, results in improved performance. The other part of Dunlosky's work is looking at interleave practice. And here the bar chart has two sets of bars, and essentially we have got the light bars when pupils have been taught in blocks on a particular topic and either tested immediately at the end of the topic or then at some time later, essentially, the sort of test performance at a later stage. And what this shows is that when pupils study a big block of content, and then that's that topic done, and examples that I can use from my own practices for many, many years. I was teaching in a school where we taught electricity in S1 and S3 and then S5, and we did that block. We maybe did it for a whole term, but that was electricity done, and we had left that until the kids moved from sort of BGE into National 5 into higher or whatever. The sort of performance that occurs when you have got blocked work like that can result in good performance in the immediate end of topic test. But then when it comes to the exam or prelim or whatever it is, some stage later, much poorer performance. Whereas if there was interleave practice throughout and revisiting topics, they actually are likely to perform more poorly in the immediate end of topic test. But as you can see from the two dark bars on the bar chart, more or less the same when it comes to doing an assessment at some later stage. So this research was, when I was still a full-time teacher before I left to come and work for the Institute of Physics, was causing me to reevaluate how we organized our curriculum, how we ordered topics, how big the chunks were, and also how we actually built regular questioning into the work that we were doing. And I was fairly confident that having spent a career as a physics teacher in Scotland and talked to teachers around the country on many occasions, that the sort of common practice that I saw and heard about wasn't necessarily fitting in with the sort of research evidence that was becoming available through sources like Rosenshine and Dunlosky. So, having done that sort of general introduction about assessment in more general, what I would like to do is to move on to look at diagnostic questions, or as they're sometimes called, hinge questions. I don't think the actual definition of hinge question and diagnostic question are significantly different. So I know that some people commonly refer to hinge questions as well. And that means that diagnostic questions are focused on understanding. We want to understand what the kid thinks about a specific idea. And in physics, we've got lots of abstract concepts. So actually trying to get an understanding of the pupil's ideas about these abstract concepts can be quite difficult. And that's the main difference that I see between diagnostic questions and the normal sort of assessment that I often got kids to do in my career, where we got to the end of topic, we did a test, they got 60% or whatever it was, and we moved on. Diagnostic questions are very much about probing understanding. And in actual fact, in the United States, they often use the term probe to actually mean tests and questions. At one of the recent IOP Scotland online sessions, Rachel Dance up in Tain was talking about using rubrics, and the fact that a rubric is just the American word for a mark scheme. Well, in many cases, you'll come across in American science and physics education literature about probes, and essentially all that they're meaning are tests and questions. It's just the word probe to me starts to conjure up, other images and rubber gloves and such like. However, we'll stick to looking at diagnostic assessment today. To try and identify the alternative ideas is absolutely key. And again, sometimes they might be called misconceptions or alternative conceptions. Again, sometimes people have got an objection to using the word misconception. But I think, as we all know as physics teachers, the sort of folk physics common sense view that pupils or any human being comes up with about an explanation for a physics concept is often at odds to the actual scientific understanding that we've got. A common example I could give is that it's a common idea that heavy things fall faster than lighter things, and in everyday experience, pupils know that a stone falls faster than a feather, for example. But of course, as physicists, we know that it's not just the gravitational force that's affecting that, but the air resistance force, and things are a little bit more complicated. So we need to actually sort of try and tease these ideas out when it comes to our diagnostic assessment questions. And that means that when we ask a question, any question, and we look at the answer that a pupil gives, what we're actually doing is making inferences, that we're trying to come to some sort of understanding that if we ask this question and pupil X says this answer, we're making an inference about what the pupil's understanding is that has led them to that answer, whereas pupil Y might have given a different answer, and we can therefore make inferences about what thought processes have gone on that lead them to get to that particular answer. And the success that we want to aim for when it comes to asking diagnostic questions is to ask diagnostic questions where we can be much more confident, or as confident as we can be, about what that inference actually is. So I'm going to move on to use some examples just to get you thinking about what sort of inferences you as a teacher will be making when you see a pupil giving a particular answer to a particular question. So my first example is a very simple arithmetic one, hopefully something that everybody can feel confident tackling. And this is where I would like you to use the chat box, and I'm going to give you a few minutes to do this, and like Alan will be helping out monitor what's going on. But my question for you is what inference are you making about the understanding of the pupil if they have answered question A? What inference are you making about their understanding if they've answered question B? And likewise for question C or question D. So I'm going to give you a few minutes for this, but I would like you to see if you can write down what you think has actually been going on in the pupil's head when they give these answers. Now, I don't think we're going to have enough time for you to do all four, but hopefully if some of you start with A and some of you start with B and some of you start with C, etc., we'll get a mixture of responses. Right, thank you. I can see there's lots of different responses coming in. And again, a certain amount of commonality, as I would expect and hope for this topic, that certainly some of the wrong answers would imply that the pupils have mixed up the operations of multiplying and add. You know, A, for example, if you've got 4 plus 4 plus 4 equals 12. So if the pupil either doesn't know or is confused the actual multiplication symbol with the addition symbol, or is confused about what the two processes actually mean, that's a possible answer. I think some people are identifying that some just haven't been able to count, and certainly I think answer B, the 3 times 3 equals 9, It might just be a rushed answer, or it might be something else that the pupil has failed to see that it's a rectangle and not a square, and come up with the wrong answer. So again, I would hope that you would all see from going through this process that although, as with all multiple choice questions, there is the correct answer and a number of distractors, and the distractors are written in order to be the sort of common wrong answers that pupils might give. You know, and writing a good multiple choice question is a skill and an art all of its own. That's based on then writing a question where there's a certain assumption about what these errors are going to be, what the misunderstandings are going to be. And this is a very simple one, simple arithmetic one. You'll see that the website that I've listed there is diagnosticquestions.com. That was a website set up by Craig Barton, also known as Mr. Barton, who does an excellent podcast. The content, I would say, is excellent. The length of the episodes is perhaps not, in that they frequently go on to 2 or 3 hours. And while many of them, and the initial ones, were very much focused on maths education, he's interviewed lots of leading educationalists across many spheres and not just maths. So I would recommend, if you have a few hours to kill, that you have a look at the Mr. Barton's Maths podcast website. And if you are looking for pre-made diagnostic questions, although it started off as a maths site, it's expanded into other subjects, including science and physics. So let's come a little bit closer to home and have a look at a physics question. And here we have got a simple question, and again, standard sort of format that you might get in a physics question paper or test. We've got a stem and we've got a supporting diagram, and we have got a simple multiple choice question. Having been given information about ammeter A1, we're asked to predict what the reading is on ammeter A2, and we have got 4 answers. So I would like you to, again, similar process to what we've just done. What I would like you to do is consider what inference you're making about the student's understanding who has chosen answer A. So in your chat box, if you could start off your answer by A and then give your explanation, please do that. But similarly, have a think about B, or C, or D. Okay, so again, hopefully we'll get a mixture of responses, and I would like you to think about what you think as a teacher the pupil's understanding is from each of the answers. Thank you very much. Lots of answers. Again, common theme. And I say, I don't think it needs anybody to have taught electric circuits very many times to realize that the common misconception that many kids have is that current is used up in a circuit. That obviously we would want to make sure that they understand that charge is conserved, current is conserved in a a series circuit like this, but there is confusion over the different electrical concepts: current, energy, charge, potential difference, and in the minds of many pupils, these get mixed up, and certainly the idea of current getting used up in some way is very prevalent. But we're still making inferences, perhaps based on a few years' experience of, teaching this topic, finding what sort of responses you get from kids when you ask that question. But we can be more certain, because a simple way of adapting a simple multiple choice question like this is to add a second tier. So rather than just having the simple, here's the question and your selection of answers for part A, which is basically describing what the ammeter will read, the part B is then giving a little bit more of an explanation. So this means that what you could be asking, and again, this is the sort of question that you could display in class, display up on a screen using a projector, and with mini whiteboards, get the kids to then just write up which two letters do you think are the right answers. So that, they might go A, B, or C, or whatever it is, and come up with an answer. Now, one of the clear important aspects of answering a two-stage question like this is that there needs to be a plausible part B for all the options in part A. So it does require a little bit of thought and careful writing to make sure that both parts actually fit together well. But what I would hope that you would now see, okay, is this slightly rhetorical question that I've asked. Does the second tier enable inferences to be made with more confidence? I would hope that the answer to that is yes. That we would hopefully be able to pick up on whether current is used up in the bulb or not. Now, one of the sort of really good sources of information, if you haven't already come across it, is when it comes to pupil misconceptions. A lot of the sort of seminal work on this area was conducted by the late Ros Driver, based at Leeds University in the 1980s and 1990s. And a distillation of all that was published in the Making Sense of Secondary Science book, and there's a folder which goes with it as well. And what I've actually put up on screen here is essentially I've just done the cut and paste from the section about electric circuits, and it shows that there are a number of key models, and there's a sort of graph in here which shows for different age ranges what the likely understanding and models are for pupils. And for basic electric circuits, the common models is, first of all, the one where you've just got a single wire. And if anybody's plugged a table lamp into the wall, it's, I think, unsurprising that young children might come up with the idea that you only need one wire to make the lamp work. They're obviously not aware that the flexes have got 2 or 3 cores inside them. So also the common misconception, as many of you have identified in answering my question, is that the current is used up in some way. And that's the one in the top right there. And then there is the correct scientific understanding, which is the bottom right. However, another common misconception that pupils have about electric circuits is that what's called the clashing current model. And that is that basically current comes out from both sides of the battery or cell and goes around, and the reason why the lamp lights is that it clashes together and gives off light. And in that case, our diagnostic question that we have just done wouldn't actually show up that misunderstanding, because there a pupil might think that the current is the same in both sides of the circuit, and the second tier hasn't had an option that has actually differentiated that from the correct scientific viewpoint. So again, having an understanding, as I said, going back to some of the sort of seminal research and making sense of secondary science is a really good single place to start. Actually gives you a little bit of the background about some of the common misconceptions that people have about common things like circuits, Newton's laws, etc. Thank you, Alan. You've been obviously busy online. So, having identified these diagnostic questions, there are obviously different ways that we can go about developing diagnostic questions. There are obviously ones like the diagnosticquestions.com website that are already available. It might be that, you know, as a teacher, you've identified that there's a topic that you're teaching that you know pupils are likely to have difficulty with, and you can write one from scratch. Or of course, there's a halfway house, and that is take one that's already existing and modify it if it doesn't quite meet your needs. So, as well as diagnosticquestions.com, where are some of the best places to start? And this is something that the Institute of Physics has actually been working on now for some time. And if you go onto IOP Spark, on the menu bar along the top, and my image here is now a little bit out of date because there's the COVID-19 menu along the top here now as well. But on the original menus along the top, there is a section on misconceptions. And there have been teams of people working at IOP to go through the physics education research literature and identify from the literature what the common misconceptions are. Robin Miller from York, again, expert in this area, has been assisting with that work. And at the moment, there are only the electricity and magnetism topics and forces and motion topics there at present. But there will be sections on the other physics domains. The Institute of Physics, in its wisdom, has decided to split physics up into 7 domains. And if any of you have been at any of the events when I've been handing out post-it notes or rubbers or things recently, you'll have seen the little images that are used to identify the 7 domains. The work for the light, sound and waves, I think, is almost complete, and that should be going live soon as well as one of the other topics. And there is also ongoing work at the moment, which is likely to go live towards the end of this year on the Earth and space topic. I've actually been involved with the light, sound and waves and the Earth and space work myself. So again, what we've been trying to do is to distill the main misconceptions and misunderstandings, not just identify them, but also identify what the research says about them and what strategies might exist to actually address some of these topics. So here's an example of what you'll actually find when you go on to the misconceptions. The very first one at the top with the forces in motion is about the confusion between acceleration and speed. Again, not something that I think should come as a surprise to anyone who's ever tried to teach speed and acceleration to any pupils. But again, that highlights the research background behind it, and also there are sources of diagnostic questions. Many of them have been taken from the best resource. I've got a sort of paper copy of some of them here as well, but there are many on the website. Again, it's hosted by the STEM Learning Centre in York, but the actual group that have produced that is based at the Science Education Group at the University of York, and I would strongly recommend that you go on there. The actual number of diagnostic questions is being added to all the time. Initially, there was a relatively small amount, but there's now a very large bank of questions that you can use. And again, most of them, I think, I would be reasonably confident that you can use straight off. It's just a case of matching them to the particular topic that you are teaching. However, you might well find that despite the sources that are there, that there isn't anything that quite meets your need, and that means that you might need to look for other sources of advice. Now, I've already said about the Making Sense of Secondary Science book is a good source of the basic misconceptions, etc. But there are other sources out there, and once you've done that, you need to decide on the most appropriate type of question. So let's have a look at some of the other sources that might be available first, and then we'll look at some of the different question types, because it's not just multiple choice. So research into pupils' thinking. Another one of Rosalind Driver's key books is the Children's Idea in Science. Lots of really useful things in there, and I would strongly sort of recommend that. But there are lots of other sources that you can get readily online and elsewhere. And in many ways, one of the key ones for teachers in Scotland is to have a look at the examiner's report. Every year, well, I'm going to say every year, but not this year, there has been a report on the exams, and here it actually highlights which questions pupils had most difficulty with. So again, that's a good source of ideas for you then to go and think about. Here was one from the 2016 National 5 that pupils got confused about the pressure exerted by a cuboid with different area sides. Again, it would suggest here that they just worked it out from the orientation that was shown in the diagram without actually thinking through the fact that if the cuboid was moved to the position where it was sitting on its largest surface area side, that would exert the lowest pressure. So again, it's something that you might then think, well, that's something that I can ask a reasonable question about, just to see how the pupils are understanding the link between force, surface area, and pressure. So if you have got an area and you want to write a question, as I said, you don't have to just stick with simple multiple choice. They're very useful, really quick to mark. Again, it's the sort of thing, if you project up on screen, you can use mini whiteboards, show me boards to get responses really quickly, just to get a feel for what the general understanding is in the class. And I've already explained a little bit about the two-tier multiple choice questions, quite often aiming to look at some sort of description in the first part to describe what's happening, and then to give an explanation of why that's happening in the second part. But there are other types of questions as well, many of them actually fairly closely related to multiple choice, and how that gives different options for the pupils to choose. So if we move on to another topic, here we've got some information about how we see, and again, there are common misconceptions about how we see. Going back to the Arabic scholars, the idea of light as being something that emanates from the eye. So rather than being the eye being a sensor, that the eye is a source of light is a common misconception. So there's some diagrams from the driver book that I showed earlier. And here is a multiple choice question that you might ask. So I'll give you a minute or so just to read the question so that you can see what's going on. Just for sort of clarity, we do have someone in a sort of den in an understair cupboard. There is a mirror there. There's also a cat in a basket. And it talks about going into the cupboard and switching all of the lights off, and then describing what you would see. So again, I'll give you a minute just to read that properly. So in this question, we're presented with a 4-option multiple choice. And again, you could use that as it stands. But one of the other techniques that's recommended to give you more information about pupils' understanding is to use what's called a confidence grid. And here, rather than just asking what's the right answer, what you're asking the pupil, the learner, to do is to give an answer for each of the options, rating them from being really confident that this is right to being really confident that this is a wrong answer. And now there is evidence as well that one of the benefits of a question like this, it's to do with what's called the hypercorrection effect. That often if you've got a pupil who is very confident that they know the answer, but that is the wrong answer, if you can then provide them with evidence that their thinking is wrong, and then they swap to having the accepted scientific understanding, that they're much more likely to learn and retain that, and much less likely to revert back to their previous misconception. Again, some of the research would suggest that we never get rid of the sort of folk physics misconceptions. We just layer the sort of accepted scientific understanding on top of that. And under times of pressure, such as in a terminal exam, it's all too easy for pupils to revert back to the folk physics idea and therefore get what would appear to be simple questions wrong in the heat of an exam. But the hypercorrection effect would suggest that if you can actually take them through that process and show that where they were confident with a wrong answer, that they were wrong, and get them thinking in the more accepted scientific way, that's likely to stick. So again, by using the confidence grid, you can get a feel for how well the pupils are actually understanding the topic. Again, using show me boards or something, you can get data like this sort of fairly quickly as well. And another similar one, I'm sure you've all seen talking heads or concept cartoons. Thanks to the late Brenda Keogh and her husband Stuart Naylor, they did a lot of work on this area. It's relatively simple for you to construct your own examples. And if you actually look at this carefully, here we've got another multiple choice question. We've got A, B, C, D, down to H in this case. And a benefit of this is not only getting feedback about understanding, so you can design these questions so that there is just a right answer and wrong answers, and you can get that evidence. But a major advantage of a talking heads type question is that you can actually populate it with answers that are all partially correct or partially incorrect. And then in a normal classroom teaching situation, that hopefully one day we can all get back to that, that what you can then do is monitor the discussion and monitor the chat that's going on as the groups of people actually debate and discuss the different options. And if you've got a series of options that are all partially correct, that can generate quite a lot of debate and argument, that by going around circulating the class, you can get a feeling for just exactly where the understanding of the pupils actually are. So just another technique that can be used to generate discussion, because it's only through that discussion that you can then start to probe the understanding of the pupils in a sort of an ongoing class situation. If they're all sitting there quiet, you really haven't got any idea of what's going on inside their heads at all. And a similar one, again, not expecting you to read all of that. It's basically an explanatory story, and essentially it's a sort of multi-part, multiple choice sequence as well. And here I've just expanded that out so you can see it a little bit better. Here it's on the topic of how we see once again, but we have got about light traveling in all directions from the sun, and you can see like sections 3, 4, 5, and 6 have got options. And getting the kids to then draw arrows like this or highlight or something, what sequence of explanation they use to go through this explanation allows you to see their understanding. And obviously, if for some reason their arrows suddenly flip over to the wrong side of the diagram, you can pick up on where about in that understanding they're making their error or mistake. And I've constructed ones like this for the kinetic, the explanation of the kinetic model for the gas laws and for switching circuits and transistors and the like, where not only are we hoping to teach the kids what a good multi-stage explanation is so that they can go into the terminal exam, the end of year exam and do well, but we want to then, using a technique like this, you can work out if there are problems in their understanding of the explanation, you can highlight where that actually is. And the next sort of diagnostic question is predict, explain, observe, explain. Those of you that have attended some of the Perimeter Institute workshops that myself and some of the IOP Scotland physics coaches have presented will know that this is one of the techniques that's frequently used by Perimeter Institute in the materials that they use. And it's particularly useful when you have a practical demonstration as part of that sequence so that you can actually test out the prediction that the pupil makes. So, here we have got a situation with a laser being shown at a wall, and it's about, predicting what you see. And, all good laser shows at concerts and so on are only good laser shows because there's a good smoke machine or something involved as well. So getting this idea of only seeing the beam when there is actually something to reflect off is something that pupils can have a misconception about. And it means that, you can actually set this up and demonstrate it. The good old days of having chalk blackboards to have a nice dusty atmosphere were a particularly good situation to demonstrate lasers. And next one that I've got here, type of question that you can consider is cloze exercises. Now, I think cloze exercises ought to be used with great caution. In the dim and distant early part of my career, I moved to a school where basically all of their notes were cloze exercises, fill in the blanks. And it was very much a case of try and guess the word that was in the teacher's head when they were writing the worksheet or the workbook. And as a new teacher in that department, I hadn't got a clue what was in the teacher's head for most of the blanks in some of the booklets. So, if I was having difficulty, there was no way that the pupils were going to be able to do this sort of thing. So I think when you use cloze exercises, the words that you miss out need quite a bit of thought, and it's not just random words that that you need to fill in to make sense of the task. So if you're cooking a pizza and we've got these sentences, again, just a little bit of prediction on your part so that I'm not speaking all the time. What is the misconception that we're trying to investigate in the cooking pizza example? Yeah, I see that lots of you are quick off the mark. Yeah, the common misconception. What's the difference by heat and temperature? And, very common for pupils to misunderstand that and in everyday language, get it mixed up. We need to be, precise with our physics language. So here we've got a series of 4 sentences where we can use the word heat and temperature, and it can then therefore show up very quickly whether the pupils are actually using these 2 terms correctly. And hopefully, if they're using them correctly, they have got a reasonable understanding of the actual meaning. Again, there is an inference in that part, but we're definitely in a better position than we were if we know that they're able to fill in the correct sequence of heat and temperature. And getting close to the end of the different questions now, another possible type of question, and this is starting to stray into the sort of area of open-ended questions that we now get in the SQA exams. That here we have got a picture of a solid in a liquid, a sugar cube in a beaker of water, for example, and being asked to describe what's good and not so good about these images, the diagrams. So things like particle size and things like that are obviously easy things that could be commented about. So again, carefully chosen examples can generate a bit of discussion about what's actually going on. And obviously that has an advantage of not only showing you as a teacher, if you can monitor that discussion, what the pupils' understanding are, you've got the benefit of giving them experience and practice in addressing the sorts of topics and developing the sorts of skills that they require to address open-ended questions in the final exam. So that's my quick summary of some examples of different sorts of questions. I did say in my slide earlier on that you can either use questions straight, or you can write your own, or you can adapt some. Another potential source of questions that you can use to adapt again comes from the United States, and they are the things called concept inventories. The forced concept inventory was the first one to be developed, but there's now a whole number of these concept inventories, and these are fairly well researched sort of standard misconception tests that have got multiple choice questions on the whole to allow you to assess the understanding of pupils. I've known about them for a while, but I had never really looked at them in much detail. But about 4 years ago, it must be now, I was approached when I was head of physics at Robert Gordon's College in Aberdeen to take part in a trial where staff at the Open University were rewriting the forced concept inventory into an online version to produce a diagnostic tests and tweaking the questions. So I got pupils in my own higher and advanced higher classes, and those my colleagues in the department, to complete the online tests. And that meant I got feedback on how well the pupils did. And then they tweaked the test and did a second round a year later. So we actually had an example where some of the pupils who had done it in their 5th year, the first version, redid the reworked version of the forced concept inventory test when they were doing advanced higher the following year. Now, these were our top performing pupils who had, most of them had been through the school for 6 years, taught by different teachers. It's a big department, and we would rotate pupils between staff. So it wasn't that, they'd only ever been taught by me. They had been taught over their school career by, 3 or 4 different physics teachers. And they were mixed up in the class. So it was a fairly good indication of how the department as a whole was performing, and not just individual teachers. And on the whole, these advanced higher pupils did reasonably well. I can't remember exactly how many questions there were. It was something like 33. And they were scoring generally in the high 20s. But when I got the analysis back, the ones that they were consistently getting wrong were all the ones around about Newton's third law, or Newton's third law overlapping with conservation of momentum. And it was such a stark split. There was a couple of these kids were going to go on to Oxbridge. So they were well motivated, intelligent, hardworking kids on the whole. But whatever we had been doing through our 6 years of physics education hadn't been getting over the concept of Newton's third law very well. That made me reevaluate exactly how we were doing and going on. So that was based on this forced concept inventory. here's a typical question. I just want to show you that even if you take a question from a well-recognized source, such as the FCI, that it can be easily improved. And I think if you were to stick half a dozen physics teachers in a room together to shred the questions, you would easily come up with improved versions. So this one's about dropping a stone from a single-story building. There's 5 options. And if you look at the options, they're actually doing different things. There's a mixture of description and explanation. If you remember when I introduced the series circuit example, we split the description from the explanation. And that's, I think, important, that you want similar sorts of responses and not mixing them up too much. So a D is a slightly odd one. It talks about this natural tendency for objects to rest on the surface. Again, a sort of conception that people can have from their sort of folk physics, common sense ideas that, you know, things fall down just because that's the way it is. And then option E talks about the force of the air, you know, but it was set up in the question that about you know, ignoring air resistance, etc. And you know, what do we mean by this, you know, force of air? So here's an improved version, again making it clear that we ignore forces caused by the air. It might help to include a simple diagram, again not overly complicated. Again, the whole issue about geocoding and presenting information in different ways, and so on, as another sort of, I think, session on its own. But a simple diagram just to make sure that the description of the scene in words can be you can be more confident they're correctly interpreting that relationship. I think that helps. And here we have got 5 statements that only describe what's happening. You know, following at constant speed, or you know, the speed increasing, reaching a maximum. Again, you can go through the question and think, well, what are the likely scenarios that pupils will actually come up with? But again, if we want to take this a little bit further, what we can do is put in our second tier, which comes up with an explanation about why it is that the object will either go at constant speed. You know, pupils might think that the pull of gravity is constant, therefore it goes at constant speed, or why it might speed up more, or the rate of increase in speed might change, either because you know, gravity gets the gravitational field strength gets stronger or weaker. You know, these are the sorts of things that they might come up with, and as a result, you know, the second tier needs to give, as I said previously, a plausible answer to the first tier, and you know, that can be quite tricky, getting nice concise wordings for that. So if you want to find the force concept inventory, it's available at physport.org, and you'll also find concept inventories there for other topics, you know, electromagnetism, waves, etc. There are other sources that you can get. I think this book here, Tippers, this is a book of lots of questions about different topics, again from the United States. And just to end on, just to show you the question here, that in the unusual world of physics assessment and examinations in Scotland, obviously we have the expectation that we can ask pupils about that extremely likely real world situation that somebody stands on a lift, stands on a set of scales in a lift and measures their weight. Well, it would appear that that's an entirely reasonable everyday situation for teachers in the United States as well, because there are some nice multiple choice questions with different scenarios for that as well. So with that, I think that's a suitable point for me to end the presentation part of the session this afternoon, and I'm quite happy for us to take some questions and things. So Alan, handing over to you, are there particular things that have come up in the chat box when I've been too busy focusing on other things?
Not really, Stuart. No, I think everyone's just been sitting in rapt attention. I've had my feet firmly on the desk here. There was just a couple of things. Graham Wilkes was asking about whether the PowerPoint would be shared, but I think Gregor's maybe going to talk about what's going to happen with that in a minute.
Yeah.
And Rachel was asking there, what was the title of the last book that you were mentioning there?
It's Tipper's sense-making tasks for introductory physics.
Okay. Oh, and Mr. Risbridger, no, sorry, I didn't get that one down, but when you get the email with the slides, the link to the Callahan reference will be on there.
I tried to good quality references that you should be able to follow on each of the slides, where I took a quote from somewhere else. Okay, if anybody has got any other questions or things, happy to discuss that for a few minutes, but otherwise we'll I think hand back to Gregor shortly as well.
Thank you very much, Stuart. I'm sure that went down just as well this time as it did the last time.